Tonight's video is on solving log equations. This is on page 10 of your notes packet. In this video, we're going to look at something that's almost the opposite of what we did yesterday. Yesterday we solved exponential equations, and we had to use logarithms to solve exponential equations. That's because they're inverses of each other. When we solve log equations, we're going to use exponents or an exponential equation. You'll see that in the end. But there are a couple things that I need you to keep in mind as we're going through these. We're going to finish up all of these notes today, this whole entire note packet, which is the next 2 pages. So let's think about this. If we have the log base b of x equaling the log base b of y, then if their logs are equal to each other, then x must be equal to y. That's just something to keep in mind as we're going through log equations. In this next item, I want you to just recall the 3 log rules that we learned a few days ago. We're asked to condense these. And to condense means, usually it means take 2 log terms and condense them into 1. So we have 2 logs separated by a plus sign. 2 logs become 1. The base is still b, and what we do with those arguments is we multiply them. That's the product rule. Usually we go in reverse. If we go in reverse, it's called expand. If we go this way, it's called condense. Number 2, when we have 2 logs separated by subtraction, we create 1 single log, and now we're going to divide the arguments. X divided by y. You can put parentheses around these if you want, but you don't have to. And then item number 3 is if you have a coefficient in front of the word log, you can take that coefficient and make it the exponent on the argument. So that goes away, and this is just the log base b of x raised to the nth power. And again, if you want to put parentheses around, you can. You don't have to. When we're about to solve a log equation, well, we know that we have a log equation when we have an equal sign and we have a bunch of log terms in there. You can see these are all log terms. So when we approach a log equation, the first thing we have to do, number 1, is if there's more than one log term on one side, which happens in a lot of these problems, then we're going to have to condense that side, and we're going to condense using these 3 log rules if you have more than one log term. Now the second thing is I'm going to put the 2 in between these because it's going to be an either-or situation. Either we're going to have a log term on both sides of the equation. In other words, we're going to have a log on the left and a log on the right, or we're going to have a log term on only one side of the equation. Like on item number 3, we have the log term on only one side. On the right side, there's nothing that says log. But up in number 1, there is a log on both sides. So we're going to approach these 2 a little bit differently. So it's really 2 steps. But the first thing that you have to look for is to condense one side of the equation. And then the second item says if you have logs on both sides, then we're going to keep in mind that thing that we thought about up here, that if you have 2 logs equal to each other with the same bases, then their arguments are equal to each other. The 2 logs are equal, that means their arguments. So that's one situation. The other situation says if we have logs on only one side, we have to rewrite the log equation as an exponential equation, like we did in yesterday's problem, a couple of problems. So after you've gone through these first 2 steps, you are going to be able to find values of x. But we always have to check because sometimes we'll get extraneous solutions like we do in almost everything this year. The argument of a log term has got to be positive, or else it's undefined. If you try to do a log of a negative number or a log of 0, you're going to get an error because you can't do a log of some negative number. It has to be positive. But it doesn't necessarily mean that the value you found has to be positive. You might get a negative value for x, but when you plug it into the original to check, it might make that argument positive. So you're not going to reject a value of x just because it becomes negative. So always check, because you could have extraneous roots. So question number 1. We have two log terms on one side separated by a plus sign. So those two logs become one log. And then you multiply the argument. So you're going to multiply x times x plus 1. That's equal to the log of 12. So after step 1, we see we have log terms on both sides of the equation. So if the log of one thing equals the log of the other thing, those logs can just kind of go away, and we have x times x plus 1 is equal to 12. Well, we have to distribute x squared plus x equals 12. Now we notice we have no logs anymore. This is just a pure quadratic equation. X squared plus x minus 12 equals 0. Factored into x plus 4 times x minus 3. So x is equal to negative 4 and x is equal to positive 3. So we have two answers potentially. But now we have to go plug them back in. When we check this, when we plug in negative 4, we get log of negative 4 plus the log of negative 3. And so right then we can reject this because you can't do a log of a negative number. So he is extraneous. Negative 4 is. Now we can check log of 3 is the log of 3 plus the log of x plus 1, which is 4. We're plugging in 3 into this original equation. Is that equal to the log of 12? Well, we can check that on our calculator to see. Is the log of 3 plus the log of 4 equal to the log of 12? And yes, they're exactly the same thing, so this one checks. So x equals 3 is the only answer. Number 2, we have a log equation that's a natural log, but we have two logs separated by subtraction. So we condense this into one single log. X plus 1 is the numerator, x minus 3 is the denominator, equals the natural log of 5. So here we have a situation where we have logs on both sides. So it's almost like saying get rid of those natural logs, and all we have to solve is x plus 1 over x minus 3 is equal to 5. Well, this 5 goes over 1, and you're going to cross multiply. 5 times x minus 3 is equal to 1 times x plus 1. Cross multiply. Which says 5x minus 15 equals x plus 1. Subtract x from both sides and you get 4x. Add 15 to both sides and get 1 plus 15 is 16, so x is equal to 4. So now we're going to go back and plug this in. Does the natural log of 4 plus 1, which is 5, minus the natural log of 4 minus 3, which is the natural log of 1, is that equal to the natural log of 5? Let's see. The natural log of 5 minus the natural log of 1 is equal to that decimal. And let's see if that's equal to the natural log of 5. Yep, they're exactly the same, so this one checks. So that's not extraneous. Number 3. We have to condense the left side. The first thing we see is a 2 is a coefficient, so we can bring that up as an exponent. So this is actually log base 2 of x squared. Now we have a subtraction here. So we have the log base 2 of the first argument, x squared, divided by the second argument, 9, is equal to 4. Put that in parentheses. And now we have the second situation. We have a log term on only one side of the equation, so we're going to follow this rule up here, which means we're going to rewrite this as an exponential equation. If you rewrite this exponentially, you start with a little base 2, on the base goes a 4, and it's equal to x squared over 9. Rewriting. Well, 2 to the 4th is 16. 16 is equal to x squared over 9. Cross multiply, x squared equals 16 times 9, which is 144. And if you take the square root, make sure you take the plus and minus square root of the right-hand side. So x is equal to plus or minus 12. Well, now when we check this, if we plug in a negative 12 into the original, you can see we're going to be doing a log of a negative number. So negative 12 is extraneous, because you can't do a log of a negative number. But 12 looks like it might be our answer equal to x. And let's see, does 2 times alpha window option 5 log base 2 of 12 minus alpha window log base 2 of 9 equal 4? And yes, it does. So this checks out. When you plug in x equals 12 into this equation, he checks. Number 4, I mean. Again, we have a 2 as a coefficient, so we're going to take that coefficient and make him the exponent on x. And we have a subtraction here. So we have log base 4 of, this is the quotient rule, x squared is on the top, x minus 3 is on the bottom, and that's equal to 2. Well, this time again, the word log is only on the left-hand side, so we're going to have to rewrite this exponentially, which says 4 to the second power is equal to x squared over x minus 3. Well, 4 to the second is 16, so I'll just write a 16 here, over 1, and cross multiply. X squared times 1 is equal to 16 times x minus 3. Distribute the 16, 16x minus 16 times 3 is 48. Now this is a quadratic, you have to set it equal to 0, so subtract 16x and add 48, and you get x squared minus 16x plus 48 equals 0. Well, what are the factors of 48 that add up to 16? Let's see, I think it might be 12 times 4. Yes, 12 times 4 is 48. 12 plus 4 is 16. But they both have to be negative to get the negative 16. So this factored is x minus 12 times x minus 4 equals 0. So in other words, x is equal to 12 and x is equal to 4. Those are our potential answers. Now let's see if it's going to make anything extraneous. If you plug a 12 in for x, you get 2 times log base 4 of 12, which is okay, minus log base 4 of 12 minus 3 is 9, equals 2. And then if you plug a 4 in, they won't make those go negative either. So I have a feeling that this is going to work. So I'm going to use my store key on the calculator to make my check go quicker. Let's see, first of all, 12 I'm going to store in for x, because I want to tell my calculator that 12 equals x. So 2 alpha window option 5 log base 4 of x minus alpha window option 5 log base 4 of x minus 3. Let's see if that's equal to 2. Yep, that's equal to 2, so that works. And now I'm going to store 4 store into x. So now my calculator thinks x equals 4. So I'm going to go back up to this equation, just highlight it and hit enter, and oh, it looks like that one doesn't check. That looks like, oh yes it does. It checks, or the value equals 2. So they both check. Silly me. both of those work. So you have two answers to question number 4. And then finishing up these problems, we've got 6 more to go. Hang in there. We have two logs separated by a plus sign, so that says ln of x times 1 equals 3.5. Well, ln is log base e, x times 1 is x, equals 3.5. To rewrite this exponentially, we start with an e to the power of 3.5 is equal to x. And so second ln 3.5. So the answer is, and did it tell me to round in any way? Oh, it says round to the nearest tenth when necessary. So we're going to have to round this to the nearest tenth. So it looks like it's 33.1. And if you plug in 33.1 in for that, it's not going to be an extraneous solution because the argument doesn't go negative. Number 6, I have a subtraction here. So I'm going to condense this into a single log. X plus 11 is the numerator and x minus 3 is the denominator, equals the ln of 3. Well, now I have the situation where logs are on both sides of the equal sign, so we can just get rid of both of those, and we're going to solve x plus 11 over x minus 3 equals 3. Well, we can cross multiply. X plus 11 times 1 equals x plus 3 times 3, or x minus 3 times 3. So this says x plus 11 is equal to 3x minus 9. Subtract x from both sides and you get 2x. Add 9 to both sides and you get 20. It looks like x is equal to 10. Now when you plug the x equals 10 back, you get the log of, or the natural log of 21, which is okay, minus the natural log of 7, which is okay, should be equal to the natural log of 3. And this will check if you wanted to check it. Let's quickly check it. Because it'll be fast. The natural log of 21 minus the natural log of 7. Let's see if that's equal to the natural log of 3. And it is. They're exactly the same. So that one checks. Now we have to condense. We have 2 logs separated by a plus sign. So we have the log base 5 of x plus 3 times x minus 3 equals the log base 5 of 16. We have logs on both sides of the equation, so we can just forget about them. And we're solving x plus 3 times x minus 3 equals 16. So we're going to FOIL this. X squared minus 3x plus 3x is 0 minus 9. If you FOIL that out, you get x squared minus 9 equals 16. And so you can add 9 to both sides, or you can subtract 16 from both sides. X squared is equal to 16 plus 9 is 25. So x is equal to plus or minus 5. Well, if you plug in a negative 5 into this equation, you're going to get a negative argument, which is rejected. So we're going to reject x equals negative 5. It's extraneous. But if you put a 5 in there, the log base 5 of 8 plus log base 5 of 2 should be equal to log base 5 of 16. So our answer, and if you wanted to check it, you could on your calculator, but I'll tell you that this one checks out also. Number 8, 2 logs separated by a plus sign. Means we're going to condense it into one single log, and we're going to multiply the arguments, x times 2x minus 1. Now let's distribute this. This says log base 4 of 2x squared minus x equals 0. Log is only on one side, so we're going to rewrite this exponentially. 4 to the 0 power is equal to 2x squared minus x. 4 to the 0 power equals 1. And this is a quadratic, so you have to set it equal to 0 in order to solve it. 2x squared minus x minus 1. Well, this is a factor in, factor out. The factors of negative 2 that add up to 1 are minus 2 and plus 1. So it would be 2x minus 2, 2x plus 1, all divided by 2. So this factors into x minus 1 times 2x plus 1 equals 0. So we have two values of x. X is equal to 1, and x is equal to negative a half, if you solve each one of those. Well, we can go back up. If we wanted to plug in x equals negative 1/2 into here, we have a negative argument here, so we can reject that one right away. He's extraneous. The negative 1/2 is extraneous. Now, if we plug in x equals 1, we would have the log of 1 plus the log of 2 times 1 is 2 minus 1 is 1. So we have the log of 1 plus the log of 1 equals 0. And that's going to be true no matter what, because the log of 1, no matter what the base is, the log of 1 is equal to 0. Natural log of 1 equals 0. Log base, what is this? Log base 4 of 1 is equal to 0. No matter what, the log of 1 equals 0 because 4 to the 0 power, e to the 0 power, 10 to the 0 power always equals 1. So our answer is x equals 1. That one checks. The next one, we have a condensing into a single log of 3x minus 2 times x minus 1 equals a log of 2x. Well, we have logs on both sides, so those logs go away, and we're just going to solve this equation with no logs. But we have to FOIL this out. 3x times x is 3x squared minus 3x minus 2x plus 2 equals 2x. This condenses into minus 5x. Subtract 2x from each side. This is a factor in, factor out. What are the factors of 6 that add up to negative 7? I think it's minus 6 and minus 1. So this says 3x minus 6 and 3x minus 1 all over 3. So this factors out into x minus 2 times 3x minus 1 equals 0. Factor in, factor out. Well, what do we have x? X looks like it's equal to 2, and x looks like it's equal to positive 1 over 3. Well, when we plug in x equals 2 up here, we get 3 times 2 is 6, and 6 minus 2 is 4. That's okay. When we plug in 2 into this one, 2 minus 1 is 1. That's okay. Plugging in x equals 2, we have the log of 4. So it looks like x equals 2 is going to be okay. When we plug in 1/3, though, x equals 1/3 up in here, 3 times 1/3 is 1, and 1 minus 2 is negative 1. So if we plug in 1/3 into this argument, it's going to make this whole argument go negative. So this is an extraneous solution. Even though x is a positive number, it's still extraneous because when you plug it in, it makes this argument go negative. It would make this argument also go negative. So you can't have that. And then the last example, we have 2 logs separated by a subtraction. So we create one log, and the numerator is x squared plus 3x. The denominator is x plus 5. Log is only on one side of the equation, so we rewrite this as 4 to the 1 is equal to, well, 4 to the 1 is just 4, is equal to x squared plus 3x over x plus 5. Put a 1 under here and cross multiply. X squared plus 3x times 1 is equal to 4 times x plus 5. Distributing, x squared plus 3x equals 4x plus 20. And now setting this equal to 0, subtract 4x and subtract 20 from each side, and you get x squared minus x minus 20 equals 0. This factors, the factors of negative 20 that add up to negative 1 are minus 5 and plus 4. So it looks like x is equal to 5 and x is equal to negative 4. Well, let's see what happens when we plug it in. If we plug in x equals 5, you know what? This is a little bit more complicated than I want. I think I'm going to let my calculator check it for me. So I'll do 5 stow into x. So my calculator, we're checking x equals 5 first of all. Now let's do the log base 4 of x squared, whoops, log base 4 of x squared plus 3x minus the log base 4, oh my goodness, what's wrong with me today? Log base 4 of x plus 5. Let's see if that's equal to 1. Yep, that's equal to 1. So x equals 5 checks. Now let's store negative 4 in for x. So now my calculator thinks x is negative 4, and let's go up and check that exact same problem. And it's equal to 1. It's not an extraneous solution. So we actually have 2 answers to this problem. X equals 5 and x equals 4. Neither are extraneous. Even though x is negative, we have 2 answers to this problem. And that's the end of this video. We'll practice a lot of this tomorrow in class.